Thanks, Fred. I appreciate it's getting pretty late now. People want to go and have their dinner. I'm the last speaker in the session, although this talk is quite appropriate coming last. After all of these talks on AI this afternoon, this talk is essentially about what you do at the end of an AI study, AI work. How do you share this? How do you communicate this? And so it's a very practical talk, but and a lot of the previous talks have had, discussed kind of big picture things, and this is more practical, although it does have some big picture relevance because, right, how do I? It ultimately is also about trust. So in the COVID era, post-COVID, we really saw how difficult it was for and important for science to better convince the public and politicians about the work that we do. Lack of information can lead to what the WHO termed an infodemic about the coronavirus. And we live in a world where next year the health secretary of the US, who controls the world's largest medical research budgets, potentially doesn't believe in large parts of medical research. And so it shows how important this issue is. And not just classical medical research, but computational research can actually be incredibly important at times. At the very beginning of the pandemic, Neil Ferguson, a computational biologist and modeler at Imperial College in the UK, produced pretty much a lot of the very first models on how the pandemic could behave. They published this in a white paper, Report 9. So they had some tools, they had some models, and this was the key data that freaked out the British government and even Donald Trump and led them to bringing in their lockdown policies. And the result of this was computational models and code became front-page news. The Daily Telegraph hounding Neil Ferguson, saying that this could be the most devastating software mistake of all time, and suddenly becoming experts on computational biology and modeling. And so this shows that bioinformatics and sharing research software can have massive implications. So this tool is called Altmetric. It's produced by a company, Digital Science, trying to be different to the impact factor and look at broader metrics in assessing research. Some of these are quite superficial, like social media posts, but it looks at news, articles, blogs, and more important things like government policy documents, patents, and things such as that, coming up with an ultimate score. So this tool, Altmetric, ranking all research over the last decade based on their metric, thinks Report 9 was the most influential, highest ranked single unit of research that came out, right? So a computational model ranked by them, they think is the most important thing that happened in science in the last 10 years. You may disagree with this, but it shows the wide, how wide these things can go. GigaScience, if you don't know us, we're the publishing unit of BGI. We have a couple of journals, and it really focuses on this reproducibility and transparency and trust issue, in that we publish and scrutinize data sets and software, and really try and throw light and dig into the nitty-gritty of these things with our journal. Reproducibility is a really important part of this. And because we have all of these key things available, we've done a lot of case studies trying to assess the reproducibility of the things that we're publishing, constantly assessing ourselves and testing ourselves and experimenting on how to share these really important things. We've published a number of papers on some of these case studies, really getting kind of putting the microscope on the reusability and reproducibility of computational research. And we've also experimented with projects such as Code Check. So this is a kind of community project coming from researchers in Europe, where they've basically mobilized an army of PhD students to scrutinize the code in published research and produce as a kind of independent, unbiased group. So it's basically some protocols and methods and ways of assessing research, and if the figures in a paper can be reproduced, they produce a certificate of executable computation. And this is useful for authors, that they can ask for one of these to be created. It can show their work works or doesn't work, but if it looks good, they can then share this independent report with a journal and maybe help the peer review kind of go more smoothly. And so we've experimented with this with a couple of papers and managed to nicely recreate the figures from the code, and got some of these reports. One of the things that the Code Check group did was they actually went back to this report 9, Neil Ferguson's code that the Daily Telegraph and all of these journalists said was a buggy mess and didn't work, and they at least managed to execute it. They actually managed to recreate the figures that are in report 9 with his code. You know, you can take the conclusions as you wish, but you can't criticize this code for not working because independent experts have at least shown that it does work. So this is the kind of things you can do to build trust and make this, you know, highly complex world run a bit smoother. We've published COVID-related research, you know, for example, immunogenomics, immunoinformatics tools, looking at cross-reactivity. This was a controversial area during COVID, you know, do other coronaviruses offer protection? One group, they produced a tool, and so this was a nice experiment for us where we actually created our first executable research article, where you can click on the article, a version of the paper comes up, you can scroll and look at each of the figures that are created from supporting code, the supporting code that was published. You can then click on a little button and scrutinize the units of code, like support, that were basically created that figure. You can even tweak, edit, and re-upload, you know, and kind of regenerate the paper, for example. Also, we embedded in the paper the whole tool that wrapped in a Code Ocean capsule. You can basically load this up, add your own data, run it on your own cloud computing account, for example, inside, you know, potentially inside the paper. So we've done a lot of work trying to make papers more reproducible, but over the 12 years we've been running, a really big challenge has popped up in recent years. It's the rise of the machines, or at least machine learning. A higher and higher proportion of our computational papers are basically using machine learning now as a method. You can see in this graph, in sort of, you know, the beginning, middle of last decade, these machine learning papers really started to rise. So CNKI shows Chinese language abstracts, and PubMed shows it in English language. So there's just this huge explosion, and we and other journals publishing computational research have just seen higher and higher proportion of our papers use machine learning. This has just made new challenges in actually assessing these things because of black boxes. Black boxes have been this kind of iceberg that's now really kind of come to the fore, that these are very complicated experiments. There are different inputs, different outputs, the models, the parameters, all of these things are essential to actually understand this. But most machine learning research, a lot of the algorithms and stuff that people are using are proprietary. This has just got a lot more complicated to try and get into these black boxes, and that causes these, you know, problems in trust and sharing and understanding these things. So this is something we've really had to tackle because we have to deal with it. We are at the front line of getting all of this research. So we've looked around, and there are a number of checklists and standards out there that have attempted to kind of throw light on these things, but they've been very focused on medical research. A systematic review found about 30-odd of these different standards, but they were very related to neuroradiology, medical imaging. People have drafted these things because they want to get things into the clinic. You have to they want to commercialize these things. The FDA and things want this kind of information. But for more general, but they're very specialist, and so as a journal publishing lots of very broad scope, we need something that's more broad, more general, will work for biology and not just medicine. And it's kind of written for taking things into the clinic. We need things that work for peer review and from a kind of journal context. And it's challenging. You need to balance these things being very comprehensive with them being unusable. You want them to be easy to use, and having online tools will make this a lot easier for the kind of Joe public to kind of use, right? We're adding new steps, and we don't want to make too many barriers. And so the standard that we have decided to try out is this one that comes from the ELIXIR, the European Union Machine Learning Group. They developed this standard called DOME, which stands for Data Optimization, Model, and Evaluation. It kind of really looks at these four key factors and asks for what they have defined as like the key information that you need to figure out how an experiment comes together, if you want to use the individual parts or find the individual parts. It's a little bit complicated, but the advantage of this one is it has a tool. It has a data stewardship wizard. And so particularly using this wizard, we have worked this into our publishing processes. This is still a bit of an experiment, but this is, if you submit machine learning research to us, this is essentially what we do. We look to see, does the paper follow DOME? Well, very few papers do, but does it look like it's potentially DOMEable? If it has no chance, then we immediately desk reject it. If it needs a bit of work, we can go back to the authors and say, show them the checklist, get them to add a bit more information. If it looks nearly there, then we send it through to the next stage. We send it to our data team, our curators, and they then send the wizard to the authors and get them to fill out all of this key information into the wizard. It's pretty easy to use, but it's asking for this key information. When they have sufficient information, they give it back to the editors. We then send it out to peer review, and we hope that this actually makes the peer review process easier. We give these forms we give the data stewardship wizard link to the reviewers so they can actually figure out how this study came together. This information probably isn't in the paper, but it's actually in the wizard. If it passes peer review, then we integrate these annotations into the paper. They ultimately have a registry that this gets stored and is searchable and stuff. And so hopefully this makes that, this is a sort of logical process. And if you want to see what the end product looks like, so at the end of the paper and the data availability, we mentioned that there are these annotations. If you go in our GigaScience database, you can see there's like a link out to the annotations. If you go to the data stewardship wizard page, they've got like metrics on how much of these things they filled, and then you can go into the individual points for all of these, and the end product ends up in the registry. It has a permanent identifier. People can find these things. It's machine readable. It's kind of more accessible, right? So this is the kind of end product, and it's useful for if you read a paper, you want the algorithm, or you want the test data, you want the training data, you want the model, you want all of these parts. This makes it much, much easier to find all of these things, hopefully making our papers a lot more useful. So on top of in the methods, taking a step back, AI is now being used in the generation of the entire papers. This image is very famous of the Frontiers paper that was rejected with the AI-generated rat that makes absolutely no sense. This has sort of led to talking about trust. This has led to a lot of mistrust in scientific publishing and the way that we do things, and this is kind of obviously what we want to avoid. But generative AI is here. Everybody is using it, writing these papers. So following the GigaScience transparency approach, we just ask for disclosure. And so If papers have used AI, we can put a summary of use section where they explain exactly how they used it. This particular paper, it's a short software note that they actually they coded the software with ChatGPT, then wrote the first draft of the paper with ChatGPT. And so we've asked for, and then obviously a human then kind of expanded upon this, and we had rounds of peer review that improved it. But if you want to see the original version of the paper, of all of these outputs that ChatGPT created, we actually put that in our database. That's all readable, and we also asked them to cite the version of the LLM used, for example. Taking this like an even higher level step, it's quite interesting that a court case that I think the New York Times took against OpenAI as to the source of their training data showed that the #1 peer-reviewed source, so they get it from many non-peer-reviewed sources, newspapers, things editorializing that aren't necessarily very factual. The most trustworthy source of training data from ChatGPT is actually PLOS, because they're open access. #2 was Frontiers, because they're open access. And #3 was Springer Open, which is basically BMC, because it's open access. So Nature, the Cell, all of these journals have had zero effect on improving ChatGPT, of improving the internet. It can be argued that these companies are like taking the publishers for a free ride and get this information for free, but it can also be argued it's a good thing that it works better, right? Like, it's much better that it has this trusted, validated information than junk. So this is just kind of something to think about, and how, and why we need to do a better job in peer review, because this junk is coming back into, if it's not properly validated, it'll actually make the AIs less reliable as well. So I've got a thing about time is nearly there. So I'll just quickly summarize that there is a need to throw light on these black boxes to increase transparency, reproducibility, reusability, and I hope I've stressed the need for trust. We've been doing this with various experiments, but yeah, we've been working with the DOME recommendations, particularly for machine learning research. We found it quite useful in the review process and publication process. It's still an experiment. We've done it for about 22, 23 papers that we've published, and we've got more currently under peer review. There may be better standards come along. This is if you submit stuff to us, but if you're writing your own machine learning papers, it's a useful thing to actually make your papers more robust. You may want to come to these things several years later, and actually you'll have forgotten where all of this stuff is, and DOME is useful to for your own self. And so, yeah, I think people want to have dinner, so I'll just say thanks to all of the GigaScience team for all of your work here, BGI for supporting GigaScience Press, our tech partners at River Valley, and the DOME Consortium as well for working with us on this project. Thank you.